50 advanced facts about vectors. Basic concepts and properties. 1. Vector spaces. Vectors are elements of vector spaces, which are algebraic structures satisfying certain axioms. 2. Linear combinations. Any vector in a vector space can be expressed as a linear combination of a set of basis vectors. 3. Linear independence. A set of vectors is linearly independent if no vector can be expressed as a linear combination of the others. 4. Basis. A basis of a vector space is a linearly independent set that spans the space. 5. Dimension. The dimension of a vector space is the number of vectors in a basis. 6. Vector operations. Vectors can be added, subtracted, and multiplied by scalars. 7. Dot product. The dot product of two vectors is a scalar quantity that measures their similarity. 8. Cross product. The cross product of two vectors in three-dimensional space is a vector perpendicular to both. 9. Norm. The norm of a vector measures its magnitude or length. 10. Unit vector. A unit vector has a norm of 1. Advanced topics. 11. Inner product spaces. A vector space equipped with an inner product is called an inner product space. 12. Cauchy-Schwarz inequality. The Cauchy-Schwarz inequality relates the dot product of two vectors to their norms. 13. Orthogonal vectors. Two vectors are orthogonal if the dot product is 0. 14. Orthonormal basis. A basis consisting of orthogonal unit vectors is called an orthonormal basis. 15. Gram-Schmidt process. The Gram-Schmidt process is a method for constructing an orthonormal basis from any basis. 16. Eigenvectors and eigenvalues. Eigenvectors and eigenvalues are used to study linear transformations. 17. Diagonalization. A matrix is diagonalizable if it can be expressed as a product of a diagonal matrix and invertible matrices. 18. Singular value decomposition, SVD. SVD is a factorization of a matrix into three matrices: orthogonal, diagonal, and orthogonal. 19. Eigenvalue decomposition. A matrix can be decomposed into a product of eigenvectors and eigenvalues if it is diagonalizable. 20. Quadratic forms. A quadratic form is a homogeneous polynomial of degree 2 in several variables. Applications. 21. Physics. Vectors are used to represent quantities such as force, velocity, acceleration, and momentum. 22. Engineering. Vectors are used in structural analysis, fluid dynamics, and electrical engineering. 23. Computer graphics. Vectors are used to represent points, lines, and surfaces in 3D graphics. 24. Machine learning. Vectors are used to represent data points in feature spaces. 25. Optimization. Vectors are used in optimization problems to find optimal solutions. 26. Control theory. Vectors are used to represent state variables and control inputs in control systems. 27. Quantum mechanics. Vectors are used to represent quantum states in Hilbert spaces. 28. Signal processing. Vectors are used to represent signals and systems. 29. Game development. Vectors are used to represent positions, velocities, and orientations of objects in games. 30. Data science. Vectors are used in data analysis, visualization, and modeling. Additional topics. 31. Vector calculus. Vector calculus deals with the differentiation and integration of vector-valued functions. 32. Tensor analysis. Tensors are multidimensional arrays that generalize vectors and matrices. 33. Clifford algebra. Clifford algebra is a generalization of the algebra of vectors and scalars. 34. Lie algebras. Lie algebras are algebraic structures that arise in the study of continuous groups. 35. Differential geometry. Vectors are used to study curves, surfaces, and manifolds in differential geometry. 36. Topology. Vectors are used in algebraic topology to study the properties of topological spaces. 37. Functional analysis. Vectors are used in functional analysis to study infinite-dimensional vector spaces. 38. Numerical analysis. Vectors are used in numerical methods for solving equations and systems of equations. 39. Game theory. Vectors are used to represent strategies and payoffs in game theory. 40. Cryptography. Vectors are used in cryptography to encrypt and decrypt data. 41. Control theory. Vectors are used in control theory to represent state variables and control inputs. 42. Image processing. Vectors are used to represent images and perform image analysis tasks. 43. Robotics. Vectors are used to represent robot positions, orientations, and velocities. 44. Physics simulations. Vectors are used to simulate physical phenomena such as fluid dynamics and particle interactions. 45. Financial modeling. Vectors are used to represent financial data and perform risk analysis. 46. Biology. Vectors are used to represent biological data such as gene expression profiles. 47. Chemistry. Vectors are used to represent molecular structures and chemical reactions. 48. Geology. Vectors are used to represent geological features such as faults and folds. 49. Meteorology. Vectors are used to represent wind velocity and atmospheric pressure. 50. Astronomy. Vectors are used to represent the positions and velocities of celestial objects. 50 more advanced facts about vectors, avoiding repetition. Deeper dive into vector spaces. 1. Dual space. The dual space of a vector space consists of all linear functionals on that space. 2. Quotient space. The quotient space of a vector space by a subspace is another vector space. 3. Direct sum. The direct sum of two vector spaces is a new vector space formed by combining their elements. 4. Tensor product. The tensor product of two vector spaces is a new vector space with a multilinear structure. 5. Exterior algebra. The exterior algebra of a vector space is a graded algebra generated by the wedge product of vectors. 6. Clifford algebra. Clifford algebra is a generalization of the exterior algebra that includes both the wedge product and the dot product. 7. Jordan canonical form. The Jordan canonical form of a matrix is a block diagonal matrix that reveals its Jordan blocks. 8. Singular value decomposition, SVD. SVD can be used to solve linear systems, compute pseudo-inverses, and perform dimensionality reduction. 9. Principal component analysis, PCA. PCA is a technique for finding the principal components of a dataset, which are the directions of maximum variance. 10. Kernel and image. The kernel of a linear transformation is the set of vectors that map to zero, and the image is the set of all vectors that can be obtained by applying the transformation. Advanced applications. 11. Quantum computing. Vectors are used to represent quantum states in quantum computing. 12. Control theory. Vectors are used to represent state variables and control inputs in control systems. 13. Image processing. Vectors are used to represent images as matrices, and image processing operations can be performed using